Hey guys, Mr. Backerberg here. In this video, we're going to look at continuity at a point. So any function y equals f of x whose graph can be sketched in one continuous motion without needing to lift up your pencil is considered a continuous function. So we're going to take a look at an example where we're going to investigate some continuity. So as we look at this graph down in the bottom right hand corner of our screen, that's just representing some function f. And if we look at the picture, we notice that there are a couple of breaks in the function. So as a whole, this function is not necessarily continuous because we couldn't draw this graph in one smooth motion without needing to lift up our pencil. But we can talk about certain places on the graph where it is continuous and other places where maybe it's not continuous. So as we're looking at where this function f is continuous, I'm going to read my graph from left to right. And what we've got happening here is we do have a nice connected line going from that x value of 0 over to the x value of 1. So we could say that our graph is continuous on the interval from 0 to 1, but then there's a break, so that's called a discontinuity. So there's a discontinuity at that x value of 1. But then again, if we look at the graph, there's a smooth connected piece between 1 and 2, so it's continuous between 1 and 2, but then we've got another discontinuity. There's a break in the graph at that x value of 2, so there's another discontinuity at x equals 2. But then as we look at the rest of the graph, that is all smooth and connected. So it's continuous from 2 until we get to that x value of 4. So really, there's 3 continuous chunks of our graph, but there are 2 breaks in the graph, 2 discontinuities in the graph. Now, there is another way that we could talk about this. Instead of talking about all of the individual places where it's continuous, we could say that this function is continuous on the interval from 0 to 4, so that would be on the whole graph, except at x equals 1 and at x equals 2. So these two things are saying the exact same thing, talking about all of the individual intervals where it's continuous and where those 2 discontinuities are happening, or just by saying your entire function is continuous except for the break at 1 and the break at 2. Now, talking about continuity at a specific point. If we're talking about an interior point or a point on the inside of your graph, a function y equals f of x is continuous at an interior point c of its domain if the limit of your function as x approaches c is equal to just f of c. So whatever that function value would be if you plugged c into it. Now looking at the end point of a graph, a function y equals f of x is continuous at a left endpoint a if that limit of the function as x approaches a from the right-hand side, if that is just equal to f of a, or it's continuous at a right endpoint b of its domain if the limit of your function as x approaches b from the left-hand side is just equal to f of b. Now, if a function is not continuous at a specific point, then we would say that our function is discontinuous at that c value, and c would be called a point of discontinuity of the function. So as we're taking a look at this example, we're going to talk about some points of continuity and some points of discontinuity for the greatest integer function. So the greatest integer function is this flat stair-step graph. And basically what the greatest integer function does is it takes whatever number you're plugging into it and rounds it down. Some people also call it a floor function because it's rounding down. Now just by looking at the graph, I can see that there are all of these different chunks of the graph that are not connected in one nice smooth line. So there's some discontinuities happening there. So let's talk about one of the discontinuities first. And let's say we wanted to focus on the x value of 3. And let's talk about it in terms of some limits. So as we do the limit as x is approaching 3 from the left-hand side, we're going to be focusing on this segment of our graph right here. So we're approaching 3 from the left-hand side. Now this is a flat horizontal chunk along the y value of 2. So the limit of our function, of this integer function, as x is approaching 3 from the left-hand side, that's just equal to 2. But if we look at the limit as x is approaching 3 from the right-hand side of our greatest integer function, well, if we're approaching 3 from the right-hand side, then we're focusing on this chunk of the graph up here. So approaching 3 from the right-hand side, we're along this flat horizontal chunk at a y value of 3. So that limit is at 3. And then if we look exactly at f of 3, well, if I plug 3 into an integer function, 3 rounded down is just 3. In order for this function to be continuous at 3, the limit as we're approaching 3 from both sides would have to equal the same value in order for the limit to exist, and that value would have to equal whatever f of 3 is. So we're okay as we're approaching 3 from the right-hand side because that limit of 3 matches up with the function value of 3, but as we're approaching 3 from the left-hand side, that limit was 2, which is not equal to that function value, so this limit does not exist because of that break in the graph. So that kind of helps describe the behavior around that discontinuity at 3. But if we wanted to talk about a place on the graph where it is continuous, if we just look at one of these flat horizontal chunks, and maybe let's just look at an x value of 1.5. So if we do all of this kind of same work, if we look at the limit of this function as x is approaching 1.5 from the left-hand side, well, 1.5 is right in the middle, so we're focusing on this flat chunk. As we approach 1.5 from the left-hand side, we're still along this flat horizontal chunk at the y value of 1. But then if we do the limit of this function as x is approaching 1.5 from the right-hand side, so if we start at 2 and work our way in, again, we're along that flat horizontal line at the y value of 1. So both of those have a limit of 1. And then if we look at just the function value, if we do f of 1.5, well, plugging 1.5 into this integer function, the integer function rounds that down, so 1.5 rounded down is just equal to 1. So these two limits are matching up, and it's equal to that function value. So that describes the continuous behavior around that x value of 1.5. Now there's a few different types of discontinuities that we could see within our graphs, and the first one that we're going to talk about is a removable discontinuity. So if we had a graph of a function, and if there was a hole in the graph where that point along the graph was literally just taken out of there, it was removed from there, that is a removable discontinuity. Now, with a removable discontinuity, that point could be taken away completely, like it is in that first picture, or that point could just be shifted to a different location. So here we've got a hole in the graph, and that point just got shifted up to 2 instead of being at 1 like it's supposed to be. That also counts as a removable discontinuity. There's a hole in that graph, and that point was just taken out of there. Both of these represent removable discontinuities. Another type of discontinuity is a jump discontinuity, so where there's a big gap between the two segments of your graph. So this is kind of like your greatest integer function, where it's jumping between all of those different integer values. The next type of discontinuity is infinite discontinuities. So as you're approaching a specific value, if your graph grows boundlessly to positive infinity or even down to negative infinity, it's discontinuous there because of that infinite behavior around that specific x value. Also, for discontinuities, you could have something called an oscillating discontinuity. So as you're approaching a specific point or x value, your graph could be oscillating, bouncing up and down between y values. So it's not really approaching a specific y value, but it's just constantly bouncing up and down as you get closer and closer to that x value. That's oscillating discontinuity. Now there is a way that we can make some adjustments to a function that actually will help us remove a discontinuity from it. So we're going to take a look at the function f of x equals x squared plus 5x plus 6 over x plus 3. And the first thing I want you to notice about this is that it's a rational function. It's a fraction. And anytime we're dealing with rational functions, the domain is going to be important to us. And as far as this function goes, because it's a fraction, it would not be safe for us to plug -3 in, because if we did, that denominator would be 0. But actually, we can do some factoring in the numerator here. If we think sum and product factoring, that numerator is going to factor into x plus 2 and x plus 3. And then with that x plus 3 on bottom, those x plus 3's will actually cancel each other out, leaving us with just x plus 2 as kind of the simplified down version of that function. But when we do this simplifying, our function holds on to any domain restrictions that we put on it at the very beginning. So it's this function x plus 2, but we're still not allowed to have an x value of -3, because if we look back at the original function, -3 is not defined, because that would give you 0 on the bottom of your fraction. So if we were to graph out this original function, it's going to end up looking like the graph of the equation x plus 2, but there's going to be a problem at the x value of -3. So in my calculator, I've got that original function typed in. I'm going to do zoom 6 to get my nice 10 by 10 window. We said that it was going to look like x plus 2, so a line with a slope of 1 going through that y-intercept at 2. And our graph does look like that. But I said there was going to be a problem at -3. But our calculator doesn't really show that problem visually. If we look at that x value of -3 along the graph, it doesn't look like anything bad is happening. But if we look at the table instead, so if I hit second graph, that'll bring up the table, I can see that we've got an error happening at -3 because of that undefined value from our original function. So I'm going to sketch out kind of a representation of what's happening here. We've got our graph, and it looks approximately like a line with a slope of 1 with a y-intercept at 2. But at that x value of -3, there's a problem happening in there because of that initial domain issue. So what's really happening there is there's a hole in your graph, but your calculator has trouble showing it. So that's a removable discontinuity. We removed that point from the graph. But what we're going to try to do is write out a different function using this original one that we were given, but I want to fill in that hole in the graph using another piece. So what we're going to do is write out a piecewise defined function, and I'm going to call it g of x. Now for the first part of the function, I'm going to leave it defined as what our original f of x was. So I'm going to define it as x squared plus 5x plus 6 over x plus 3. But because we've got a domain issue happening at -3, we're going to use this for all x values that are not -3. But then what we want to do is define a second piece of our function, which will help us fill in this hole in the graph so that we do end up with a continuous graph. So what we would want to think about is, where would that point be located along this graph if it did exist? So that's where the simplified down version of this function is going to come into play. If we ignore the initial domain restriction, it would be safe for us to plug -3 into this simplified down version. And if we did that, if we plugged in -3, we would get an answer of -1. So for the second piece of my function, I'm going to define that as the function -1 if we're talking specifically about the x value of -3. So then what that gives us, this top piece of our piecewise defined function would give us that graph with the hole in it, but by defining a second piece at -1 for the x value of -3, it kind of fills in that hole. So with those two different pieces of that piecewise defined function, we have created a continuous function out of this original function that initially was not continuous. This process that we just went through is called coming up with an extended function. So we could say that this function g that we just came up with is a continuous extension of our function f that we started with. That's going to be it for this video. Thanks for watching.